the high, the divergence induces the low at the surface, and the convergence in the upper levels of the atmosphere inducing the high at the surface. So those waves in the upper levels of the atmosphere, both these illustrations at the bottom are showing the 500 millibar level, so that's above that level of the upper levels of the atmosphere. Those waves, whether they're troughs that we were looking at in the previous slide or even ridges, those are called long waves. And when you go from one trough to the next or from one ridge to the next, that is one long wave in the atmosphere. So upper level winds flow from west to east, and they are known as the upper level westerlies. A zonal flow is nearly due west to east, while a meridional flow has a north to south component to the wind direction. Waves that develop in the westerlies allow for the transport of cold air south and warm air to the north. Those long waves have a length of many thousands of miles, the wavelength from trough to trough or from ridge to ridge, crest to crest, and move quite slowly. Now, embedded in the long waves are these little short waves, or just disturbances, and they move more quickly, but they also move within the long wave pattern. And as that little short wave, and you can see that in the illustration in the left, as those short waves move to the long wave pattern, they tend to deepen troughs, making the troughs dig deeper, and you can see that from day 1 to day 2, where that short wave way out over the Pacific digs into a trough, and by day 2 we've got a nice deep trough over the west coast of the United States. And then also, as those short waves move into ridges, they tend to weaken. So short waves move into troughs and they deepen the long wave trough. Short waves move into ridges and the short waves themselves weaken. Now look at day 1 and day 2 with short wave number 3, the one over on the east coast. As it's moving into the long wave trough, it's not very big, and then as it digs into that long wave trough, not only does it intensify, but it also deepens that trough. And the reason why we have the isotherms on day 2, the 10 degree, 20 degree, 25, and 30 degree below zero red dashed lines, those isotherms, are to show how those upper level winds cross the isotherms as those lows deepen, meaning a north wind is now going to push that cold air to the south on the entrance region of the trough, and then on the exit region of the trough, that warm air is going to push that southerly flow is going to push that warm air to the north. And that is how we get the cold air and warm air advection in the upper levels, forcing the cold air and warm air advection in the surface. In addition to the long wave troughs and ridges in the atmosphere that provide directional convergence and divergence, with the convergence in the upper levels happening in the entrance regions of the trough, and the divergence in the upper levels happening in the exit regions of the trough. We also have these cores of faster moving winds within the westerlies, and those westerlies are the jet streams, and the cores of faster moving winds are known as the jet streaks. So the jet stream helps to deepen cyclones with divergence aloft and build anticyclones with convergence aloft. And where the air converges on the surface, you get the anticyclone. Where the air diverges in the upper levels of the surface, you get the cyclone. But within the jet stream is a core of stronger winds known as the jet streak. And in this particular illustration on the left, now where the winds are speeding up in that jet streak, that area of maximum winds, also happens to be in the exit region of that trough. And that literally enhances that lift, because not only do you have directional divergence in the exit region of that trough, but you also have speed divergence, where winds are going from slower speeds to much faster speeds. And so air converges at point C in the entrance sector, forcing cold air to sink and the high at the surface to build, so the anticyclone at the surface to build. And then air diverges over point D in the exit sector of the jet streak, causing air to be pulled up off the surface and deepening that low, or deepening that cyclone at the surface. And so you can see with this right-hand illustration, just your typical trough in the upper levels of the jet stream, and a couple of things happening. Yes, the convergence and divergence creating the surface high and low, but then look at the low from day 1 to day 2. Over Michigan on day 1, but then moving into northwestern parts of Canada as we move into day 2. That low, that mid-latitude cyclone, is following the direction of the jet stream itself, that long wave trough. It's following that same direction, and at about half the speed of that long wave trough. And you can see from day 1, an open cyclone, to day 2, where it is at its occlusion and has moved through the deepest point of that cyclone, where now the occlusion is occurring and cold air is lifting the warm air up. So you don't have as much of a temperature difference at the surface. Now you're getting into a weakening cyclone. So here again, a reiteration of our developing mid-latitude cyclone or extratropical cyclone. In A, we have a nearly zonal flow in the upper levels, lying almost parallel to our surface stationary front, which in this case would be our polar front. To the north of the polar front in A, we have the polar easterlies. To the south of the polar front in A, we have the westerlies at the surface, warm from the south, cold from the north. And our long wave pattern is nearly zonal in the upper levels of the atmosphere. Move to B, and in the upper levels of the atmosphere, now our long wave pattern, a trough has begun to develop. The reason why this trough has deepened is because the flow at B is disrupted by a short wave. Now, the short wave is not shown in this particular illustration, but a short wave moves into that trough, deepening that trough in the upper levels of the atmosphere. And again, north winds now cross over those isotherms, so they'll begin to push cold air south and lift warm air to the north. So the short wave induces that trough in the long wave pattern. Cold and warm air advection at the surface begin that cyclogenesis at the surface, or the beginning of the cyclone at the surface. Cyclogenesis, the development of the beginning of the cyclone. As that trough deepens in the upper levels due to the short wave, vertical motions in the atmosphere are produced which are required for the extratropical or the wave cyclone to form. So those vertical motions are the downward air in the entrance region of the trough because of convergence at 1 in B, and then in B in the upper levels at 2, divergence aloft, creating the upward motion and enhancing our wave cyclone. And of course at C, you can see where the occlusion has begun, so now we're at the most intense portion of the cyclone. But in this situation specifically, our long wave pattern breaks down a little bit and that upper level low forms. Now, with that upper level low directly over our surface low, we have convergence. Remember, low pressure at the surface is and aloft is convergence. So now, at 500 millibars, we have convergence and convergence at the surface. Well, that convergence in the upper levels is now going to begin to force air to sink, all right? And that is going to then weaken that cyclone. And so this is one way that weakens cyclones, as you get these upper level lows on top of them. If you move back to B, I want you to notice that the upper level low and the surface low are not vertically stacked. The upper level low, the actual purple L, is to the north and west of the surface cell. It's when this upper level low gets directly above the surface low that it causes it to weaken and fill in. So one last look at the combination of the 500 millibar levels, that upper level chart, and the surface chart. Winds aloft steer the movement of surface pressure systems. Cyclones move at about half the speed of the upper level 500 millibar flow. For a cyclone to deepen, it must have upper level support or an upper level counterpart. And that is the purple low, that upper trough, not directly over the low, but to the north and west of the low. That trough in the upper levels of the atmosphere provides that upper air support. It provides the divergence aloft required for that low at the surface to deepen. Cyclones deepen under the exit region of an upper level trough, while anticyclones build under the entrance region of that trough. Convergence aloft forces sinking air, and divergence at the surface and divergence aloft creates upward motion and convergence at the surface, or low pressure. And again, this is another chart showing you how that pattern develops and what we see at the surface. At the surface, with high pressure, cold air, and clear skies along the frontal boundary, we have showers and thunderstorms. Ahead of the warm front, we have precipitation and snow to the north and northwest of the warm front. You can look at the pressure pattern and see falling pressures ahead of the cold front and then rising pressure on the backside of the cold front. And again, out ahead of the warm front, the pressure is falling as well. And then behind the warm front, that pressure would increase until the cold front comes through. So you can see our precipitation patterns, our pressure patterns, and our wind patterns as they switch and change as a mid-latitude cyclone moves through. So this animation is a fairly long animation showing everything that we have been talking about. So if it hasn't started moving yet, you can go ahead and click that lower right-hand side. And you see high pressure or subtropical high to the south with that southwest warm airflow, the polar high to the north with that northwest cold airflow, and at the surface, the cold air advection creating the cold air behind the low and the warm air ahead of the low. And so that area of low pressure begins to form at the surface as in the upper levels, that low pressure begins to deepen, and the winds in the jet stream, we begin to see some degree, and there's that shortwave trough, and the winds in the jet stream begin to provide some divergence aloft to help intensify that low. You can see that also in the upper levels that the winds are currently crossing the isobars, where they are pushing cold air to the south, cold air advection, and then warm air to the north. Now, as that shortwave trough begins to transition and move, you can see the low at the surface is also moving with that long wave trough. And the low at the surface is moving at about half the speed as those upper level winds in the jet stream. And you can see the formation and development of the low at the surface, pretty typical open wave mid-latitude cyclone, cold air advection behind the low, warm air advection ahead of the low. So you have the warm sector of the mid-latitude cyclone, showers and thunderstorms along the cold front, showery precipitation out ahead of the warm front, and then to the north and northwest of the low, that is where we begin to see some snowfall. Here our occlusion begins, our cold front's catching up to the warm front. Here we are at the deepest, most intense part of the cyclone. But as that occlusion occurs, what's happening? Well, the colder air is lifting the warmer air ahead of it. And so around that occlusion and that low, now there's not as much of a temperature difference. And so that's why that cyclone begins to weaken. The temperature gradient is not nearly as significant. So eventually, as it progresses, the cyclone weakens and dissipates as it moves on off into the north and east. So this wraps up this lecture. The next lecture will be Chapter 9. And that will be on weather forecasting, not how to forecast the weather, but the different types of weather forecasting techniques that exist.